Welcome back. Now, we've looked at permutations with repetition. Now we want to look at permutations without repetition. Repetition. Sorry about that. R-E-P-E-T-I-T-I. No, I'm just going to rewrite it. There we go. Without repetition, that means you're not going to replace what you've taken out. So, if you say we have balls numbered 1 to 6. So that means I have a ball of 1, 2, 3, 4, 5, 6, all equal sized, and I draw a ball. Let's say I draw 2. What am I left with? I'm left with 1, 3, 4, 5, 6. Let's say then I do a second draw. And I draw 4. Then I'm left with ball 1, ball 3, ball 5, ball 6. I do a third draw. Hey, draw 3. Whoops. And draw 5. So our first draw, we could draw 2 out of 6 choices. Our second draw, we had 5 choices, and then we had 4 choices. So how many different combinations would we have? Well, we could write it as 6 times 5 times 4. We did 3 draws, and that's so 6 times 5 is 33 times 4 is 120. 6 times 5 times 4, 120. Confirmed on my calculator. So that's how many different possible combinations you could have without replacement. Starting with 6 balls, numbered 2 through that. Let's say we were working with something with, say, 15. And I want to draw 5 without repetition. So, the first choice, we have to choose 15 balls. 15. Second choice, we have 14 balls to choose from. 13 balls, 12 balls, the last choice, 11 balls. Now, multiplying 15 times 14 times 12 times 11 isn't so bad. But when you're working with larger populations and larger combination possibilities, what we can do is we can actually see that there's a hidden formula there. Let's do this math here. 15 times 14 times 13 times 12 times 11. 360, 360. So to choose 5 balls without repetition from 15, there are 360,360 combinations to choose. Okay. So if you remember the other week, I represented the idea of factorial. The factorial function. The factorial function is n to the exclamation point. And it's not on a basic calculator, just addition, subtraction, multiplication, division. It will probably be on a scientific calculator and hidden somewhere. So for me, it's hidden above the 3 with an x to the exclamation point. and that's called a factorial. So that is a way that you can multiply strings of numbers that are sequential decreasing, something like 15, no, I'm going to start with 5. 5 times 4 times 3 times 2 times 1. Five factorial is how we would represent it. And if you go through and you multiply out 5 times 4 times 3 times 2 times 1, 5 times, oops, clear, 5 times 4 times 3 times 2 times 1, I get 120. Now, if you don't have a calculator that does this, find an app online. Find a calculator app or check your calculator on your phone, actually. It probably does it. Actually, let me check mine. Let's see. I don't even know if you can see it. Let's turn my power up. Let's unlock it. And let's go to calculator. All right. It's not on this main screen. I'm going to push this. It's going to turn it. Let's rotate it. Let's hope you can see this. I'm going to look around for something, exclamation point. It's not there. I'm going to do this. There it is, down at the bottom. 5 factorial equals 120. Okay, this is the factorial function, and you can use it for any numbers. You can say, hey, let's do 10. Excuse me. So if we had something like 10 factorial, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Entering that into your calculator gets to be a pain, so that's what the factorial. It is going to go through, and it's going to multiply them all to give me 3,628,800. 3,628,800. Okay, so the factorial function comes in handy. Sorry, I just had apple crumble, rhubarb crisp maybe, both. Okay, so what we end up seeing is this factorial comes into play and is very useful when you're doing stuff with permutations. And let's say we want to look at our 15 numbered ball combinations. 15 times 14 times 13 times 12 times 11. Okay? Now, if we wanted to continue, it would look something like that. But when we're doing this, we don't want to multiply after the 11 because we're only looking at the first 5 numbers. So a neat trick would be to divide by 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 to cancel it out. So what we essentially have here is, what if we 15 factorial divided by 10 factorial. And writing those numbers out are going to be huge. I don't want to do it in this case. But what can I do? Well, 15 factorial is what we're working with, but we're dividing it by 10. How can we get 10? Well, we had 15 balls and 5 draws. 15 minus 5. factorial, giving us the 15 factorial over 10 factorial. Now these numbers, this would be going back to running things using n's and r's. Your 15 is equal to n, your r is equal to 5. So you could say n factorial minus r factorial. Just a shortcut. Let's see if it gives us the same 360,360. Okay, so 15 times 14 times 13 times 12 times 11. That's a lot to type in. What if I did 15 factorial divided by 10 factorial? I think that is a lot easier than doing all those individual multiplicative steps. Would you agree? That's wonderful. Me too. Okay. Where am I taking this, Gaffney? Where's this coming from? So, let's go to a new page. Da 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 da. You think I have a slice of paper ready, but I don't quite yet. And pause it for a minute. So permutation without repetition. This is the equation we want. We want n factorial divided by n minus r factorial. And in this case, n is the number of things to choose from. So 15 balls, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And R is order matters, no repetition. There's number chosen. Sorry. And that's number chosen. Order matters. No repetition. So, another example of this, let's say ten jelly beans drawn 3 times. So, to choose from, I have 10. N is 10. Number chosen, 3. R is 3. So, that would be 10 factorial over 10 minus 3 factorial. I have to do that subtraction first. And you can type in the calculator. In this case, low numbers, it's quick and it's easy. $720. Now what if we wanted to do something like a ball draw for 20 students? So let's say we have 250 students in class. We have 250 students at school and there are 30 prizes. How many different combinations of students without repetition? Well, n is 250, r is 30. So we have 250 factorial over 250 minus 30 factorial. How many different combinations could I get? 250 factorial, whoops. So let me write this next step. 250 factorial over 220 factorial. Okay, 250 factorial. Hope you can see this. 250 factorial. Uh-oh. Uh-oh. This calculator does not handle factorials above 250. I might have made a bad selection. Do. The numbers are too big. The numbers are too big. Oh no, I can't do it. I'm going to abandon this question. Alright, that takes me to my next example. I should have tried to work numbers out before. Lesson learned. Lottery. Okay, 649. I believe there are n equals 49 balls. R equals 6 draws. Okay? How many combinations? Without repetition. Okay. 49 factorial over 49 minus 6 factorial. Well, I know these numbers work. I've done them already. 49 factorial is 6 with, if you think of the 6, then you have 62 zeros after it. Huge number. You don't want to work with that. Divided by 43 factorial. That's the 43 factorial, 52. So we're left with that. So that is 1, 0, 0, 6, 8, 3, 4, 1, 2, 3, 4, 5, 6, 7, 5, 2, 1, 2, 3, 4, 5, 6. 2, 3. There are 10,068,347,520 combinations. That's a lot. There's that many combinations to get the 6 numbers right. And where am I taking this? Well, I'm taking this as to why we shouldn't rely on the lotto. Okay, page 3, place 11, 12, May 2020. Okay. So probability of winning the lottery. So if we look at the Lotto 649, you have balls numbered 1 through 49. There's 6 draws without replacement. So in order to win it, you have to get all 6 balls correct. So the chance of getting it first time is, well, 1 out of 49. That's not a 49. That's a 49. Times second draw, you have 1 chance out of 48. 1 chance out of 47. 1 chance out of 46. Each time you're lowering the number of balls available. You have a better chance of drawing a ball at the end than in the beginning. That's 45 times 1 over 44. So 49 times 48 times 47 times 46 times 45 times 44. Look, we got that same number, 520, 1 million, 10 million. Because it's just ones on top. $10,068,347,520. You have a 1 out of over 10 million chance of getting that correct lotto ball. So that is why we don't get lotto. The chances are so small. Yes, there's people that can mathematically decide to play and do much more complicated calculations to balance risk versus funds put in, but they're spending huge amounts of money and time to do that. The general person just goes and picks 6. Not a very good odds of winning. So how we can make this easier to represent, instead of using the n factorial, we can write it in terms of just permutation letter. Permutation notation. So permutation notation is the idea that you have the number of permutations, choices to draw from, and how many draws. Now, let me check this again and see, is this on our calculator? No. So, it's not on every calculator, but essentially it does a shorthand of n factorial over n minus r factorial. So with my calculator here, I have above the 9 an NPR. Over here I have an n, but I don't need that, I just need this one. So let's say I wanted to do I have 49 balls to draw, permutation of 6 draws. I can type that into my calculator, 49, second function, this, 6, equals what I gotten before, 10,068,347,520. 10,068,347,520. You can start to do that for every number. If you don't have a calculator, see if you can find a permutation calculator on Google. I might try to link you to one. I have to check into that. Let's say you have 5 balls and you have 1 draw. Well, what would that look like in factorial notation? Well, that would be 5 factorial over 5 minus 1 factorial. So it would be 5 factorial over 4 factorial, or just 5. So for homework, I want you to first practice doing a few of these and use them on a separate sheet of paper. What we're going to move on to after this week. And remember, this equals this. Just this makes statistical calculators work easier. They're going to be big numbers, but you should be able to find it. And I want you to look at these words. How many different ways can you order these words, or these letters? Math. Gaffney. Is